So, hello there, everybody. Today, we're talking obs. We're talking all the subtle differences, small changes leading to big changes, big differences. This is a I would say, a very dry line centric video because we're talking a dry line setup. We're talking May 25th, 2016. I love teaching about this day. I have several different presentations that I give on this day because it is, I think, a fascinating day to take a look at different things. Today, though, I want to take a look at satellite imagery, soundings, and a little bit of surface charts. But mainly, we're going to look at soundings and look at the differences, the subtle differences you get. But in just a difference of like 230, 240 miles. We're talking 3 hours of driving. It is so fast that the minute you don't realize how fast the atmosphere changes, and we're talking even less than that. We're talking maybe even 20 or 30 miles from the dry line east into the warm sector. There's so much to break down here. Let's get going. So to get started, I want to take a little bit of a moment to ground. Okay. So ask yourself some questions whenever you're looking at the atmosphere. Either you're out there chasing or you're forecasting, whatever you do. This channel is for everybody. So no matter where you're at in your weather journey, enthusiast, you're just concerned about the weather, or you're a storm chaser, ask yourself questions. What makes the atmosphere different here? Uh, are there any boundaries in play today? How will all of this impact if a storm forms? Like, how does this impact storms? So, you know, those are some basic grounding principles. Now, a couple of things. I call this Chapman Carrier Sad Wichita Day because there were two really awesome supercells on this day. And then there was like some sad storms in between those, and a lot of sad storm chasers too. There's a couple of things that I want to note just to kind of ground us before we get into the images. There's going to be a boundary north, some dry air in the middle, and the atmosphere is going to go boom in the south. Okay. I just gave away what's going to happen on this day. Why? Because I want you to not worry about the results. I don't want you to be thinking, oh, what is the result? I want you to know the result before we go into this day. Okay, so here is a satellite imagery. I didn't want to use satellite imagery before, like after storms had formed. I wanted to show what it would look like before, but we are going to look at 0Z obs. I just want to make that clear as well. So there's a little bit of a mismatch here, but I wanted to show satellite kind of mid-afternoon. Few things to keep in mind, a few things to look for. There is a dry line. You wake up in the morning. Let's just say you're starting here, just so you can kind of put yourself. We know what's going to happen today. We know where you're starting. So now you got to ask yourself a bunch of questions. Okay. So here's what the surface chart looks like on this day. There is a boundary to the north here. It's running roughly along just south of I-70, kind of going east-northeast to east-southeast. Perfect boundary orientation, especially when you take a factor in the upper level winds, which are kind of blowing out of the west-southwest. This is a really good boundary orientation because this is just right of the upper level wind direction. And if you can get a storm to latch onto this, you're going to increase the shear. It's going to be something else. Also, you have a dry line arcing south from this. It's kind of bowing out there into Kansas and then just arcing back into Oklahoma. So those are your boundaries. This is the setup. Another thing to keep in mind, low level flow. So the setup, the boundaries, we know that. The low level flow, just going by the cloud streaks here, just trying to show that off a little bit. You can kind of see what the deep low level flow is. So that's the surface setup. That's the upper air setup. Let's take a look very quickly at one more thing. Some deep layer, low level flow. The cloud streaks show that. Just bounce back here. You can see those are they reveal a lot about the low level winds. So that's where you're at in terms of where the low level wind direction is. If you are paying any bit of attention whatsoever, these are three areas you're looking at. One is that area around the boundary intersection. There's a little bit of like a cold front arcing south. It's like a little low pressure there, meso low. and that boundary then arcs northeast, northeast, and east, southeast. You have the dry line in southern Kansas. That's actually, side note, where SPC put out a 5% risk on this state. What? Yeah. So, and then you have the dry line way further south in Oklahoma. Those are the places you're looking for. And actually, by mid-afternoon, it was kind of apparent. These were the 3 areas we're looking at. Not much Q development south of that South Circle in Oklahoma. And then you can see up there in Kansas, you can see what's going on as well. So, and I'm going to kind of talk about, what's going to happen, but I'm going to reveal a few things as we go. Hopefully, show you a few really cool things. Okay. So first place we're going to look for an observation is behind the dry line along this cold front in Dodge City, because I want to show you something. This is very interesting. So here's what the sounding looks like. Let's bring this full screen. You can see that the sounding, there's that really weird thing that happens sometimes in soundings where you have like a straight line at the surface. That means that the moisture profile there is not really picking up that well. So it's going to mess up your surface CAPE. You can see surface CAPE here says 4,500, but then you have 1,900 ml CAPE. The reason for that is the surface parcel, it was recorded as being too moist, so it's showing way too unstable. That's why you want to use ml CAPE generally. That's my side note. CAPE video. So if you look at this, there's several things I want to point out. Okay, first off, let's take a look at the surface chart. You can see there's a north wind in Dodge City. You could see it on the sounding just now, 65, 80. You can see how that boundary's arcing south, that little dotted line. It actually kind of extends back to the west. It's actually a cold front of sorts. Just so you know, I should have marked the whole thing, but I'm a little lazy. I did it with just the satellite image. So let's take a look. The first thing I want to show is that there is a lot of dry air here in the lower levels. You're to the west of the dry line, so it's going to be drier here, right? It should be drier, but there's still like a pretty decent fetch of low level moisture. This is actually because of that cold front. That cold front is passing through here, and it's actually bringing moist air behind it. So that's why there is some moist air at the surface, but you can see the air behind the dry line is actually very dry. You can also see the lapse rates further back west, mid-level lapse rates are good enough to actually produce some instability back here. So, that there is a lot of going to be a lot of instability east of the dry line, right? So that's important to know. And then, you go ahead. I want to point out this too. The mid-level winds here west of the dry line at 500 are 40 knots. That's really impressive. That's really good. That's going to be plenty for supercells. Now let's take a look at Norman, the sounding for Norman. You can take a look at its position relative to the dry line. You can see that it is east of the dry line. We are way east of the dry line, so we're in the open warm sector. This is a decent read of that. And so here's what our sounding looks like. You can see instantly. Here's a problem. There is a cap. The right red arrow is pointing toward that. Left red arrow, I want to point this out too. We are east of the dry, and look at all that dry air. Look how dry it is, just above 850. That is a lot of dry air. And you can see, if you look over on the right side of the sounding area of that box, just below the right arrow, you can see how the LCL and the LFC are separated a bit. And if you look at that, and you see there's like that layer of dry air is right in between those. Your updrafts, as they're going up, they're going to hit that cap. They're going to really struggle because there is a lot of dry air being entrained into that updraft. Dry air entrainment is a thing that on dry line days you have to look for, because if updrafts are doing that, it's going to take a lot of work. You got to get those LFCs and LCLs a lot closer to get storms. But again, here you can see the lapse rates are still really good. Big time instability. We're talking 4,200 ml CAPE. Let's bring that full screen so you can see it, or 4,000 ml CAPE. Sorry, I read that wrong, but lots of instability on this day. So another thing I want to point out is those mid-level winds as well. They're 30 knots this further south. So the jet stream is weakening the further south you go. That's, you don't even need a model chart. You can already see this in your head, right? You can see it in your head. But if you look at it, wind shear, this wind shear is not bad in the open warm sector here in Oklahoma. There's actually 125 0 to 1 kilometer SRH. And that's with an east-southeast storm motion. That's not bad. That's not bad at all. And you can see the hodograph has a little bit of a, nice little bit of low-level curvature. Then it's pretty straight aloft. So just some things to keep in mind. And then also, I just want to point out one last thing over here in the Cape Sin area. You can see the surface-based Cape convective inhibition is -3. Mixed layer is -75. People will oftentimes say, well, the atmosphere is uncapped. Look at the surface. Look at the surface sin. But then you look at mixed layer and it's like -75, -100, and there's no storms going. That is because that's the one you want to be looking at. Just saying. So let's take a look at another sounding. This one is Lamont, Oklahoma. And so this, you can see, very different than where we were at before. We are right on the dryline circulation. We're in that middle kind of target here, kind of on the south side of it. And we're just right east of the dryline. We're not very far away from it. If you look, though, where Norman's temperature was in the low 80s, we're dealing with upper 80s temperatures here on the dryline where we're at. So keep that in mind as we look at this. So if you look at it, well, this sounding looks a lot different than what we just saw, right? It looks a lot different. Let's bring that full screen so we can look at it. So if you look at this sounding, the first thing I'm noticing is there's no cap. There's no cap here. Next to the dry line, we've had enough heating, we have enough mixing, we have enough moisture. There's no cap here. Absolutely none. Let me take my face away so you can see the mixed layer convective inhibition is -11. It's actually lower than surface base. You can see the LCL, LFC are right next to each other. You're going to get storms here, right? So here in north central Oklahoma, south of the Kansas border, you're going to get storms. Look at this hodograph. There's not as much low-level curvature here closer to the dry line. The low-level winds are, they're not as backed here. But you can see the surface to 6 kilometer shear is 32. The surface to 3 kilometer shear is 125. So this actually isn't even, or Holistia is 125 and 76. Sorry. But you can see here is that these shear numbers aren't actually very impressive. They're not impressive. That's interesting. That's very, very interesting. So what that tells me is we're dealing with the plains, okay? So when you're dealing with the plains, it's important to point out that you can expect the low-level winds to increase almost every time in the spring toward evening because of the low-level jet. So when that low-level jet kicks in, the low-level hodographs are going to enlarge. You're going to have a really good chance at seeing much better shear, possible tornadoes if you have a supercell going, but you have to get one first. That's important. It's very important. Another thing I want to point out before we move on here is that look at that. Look at how it's a lot more moist above 850 here next to the dry line in this region. Very different than what it was at Norman. And that's an important thing to note. The moisture is much deeper here. Those updrafts, as they go up, are not going to hit that dry air as much. They're not going to be entraining as much dry air. They're going to have a much bigger chance to go boom. Okay, so pointing out the low-level winds. So let's go to Topeka right now. So Topeka. And why are we like bouncing around these boundaries? Why aren't we getting something on them? I could pull a model sounding, but I want to use ops. I want to use actual forecast soundings. And these are where they're at in the region. Wish there were more. There's not. But so we're going to take a look at Topeka. First thing I want to note, Topeka is 81 over 68. And we're using this to assess the northern target here, where you see where the dry line in front meet, it's 87 there at Salina. So the surface temp is much different. The dew point is 71 along that boundary. There is moisture pooling there. The temperature is higher there. I just want to point that out. So what we're about to look at Topeka is not fully representative of what we're going to see later on or what we see on this boundary. It's not even as good of an environment. So first thing I want to point out at Topeka, well, because of cooler air, there's actually still a little bit of capping here. Mixed layer inhibition is minus 100 just above me. It's right there, minus 100. And then you have the moisture, though. Moisture profile is beyond 850. This is good, deep moisture north of this boundary. So there's deep moisture on both sides of this boundary. We've just established that there's good, deep moisture there. As you continue on, look at this, the shear to the north. We've already established the winds are stronger in the mid layer further north here, up here in Kansas. They're stronger. You have 30, 40 knots there. The 0 to 6 kilometer shear is 36 at Topeka. This isn't even counting what would be backed winds on that boundary. That boundary has even further easterly winds. So that's going to be even bigger down on that boundary. That's just interesting to note. And then you have your surface to 1 kilometer SRH here north of the boundary, where the winds aren't even as backed and not even as strong as they are south of the boundary, are 95, and your surface to 3 kilometer is 183. I'm having a look. Don't have the eyes I used to. It's happening. It's happening. Plenty of lapse rates, going to have plenty of instability along that boundary. And again, I'm just pointing out another thing that I do see, though, up north is there's a little bit of a weakness in the mid levels. Will that affect things? Is that present on that boundary? These are things you can't really tell on OBS. You would actually need kind of models, mesoanalysis, something like that to fill in the gaps. But that's something you want to look for on these days. We know that didn't make a huge difference because there was a very powerful EF4 tornado produced just south of this sounding, south and west of this sounding. So I want to take a look one more time. There's a couple of things that I want to point out here in the middle of the day. First off, when you're assessing moisture depth, very important. I think it's very important to point out that you want to look at the characteristics of the cumulus field on satellite. If there's a lot of cumulus further east off the dry line, that means you have deeper moisture. If you ever have a situation where there's like cumulus along the dry line and then it just disappears east, that means you've got something happening. You've got a lot of capping. That could be a case. A lot of dry air, which would be, those two kind of going hand in hand, but it could be drier up there. So you're not getting the same amount of Q. Could have subsidence, mid-level subsidence. It's just suppressing cloud development. But when these are subtle. This is a very subtle change. Look at that satellite image and you see it. In southern Kansas, there's a slight bit of difference than there is down in Oklahoma. And we know from what's going to happen is that southern Kansas is not going to see robust supercells. In fact, you can see a convective attempt going off here on the dry line in southern Kansas, and it's struggling. And the one further north, I covered it up with boundaries, but it's much more robust. And the one further south, when you saw it later, much more robust because better moisture, less capping, all the things, okay? Here's the, and you can see it. I just want to point this out. You can see how on the 850 analysis at 0Z, I'm just going back and forth here. You can kind of start matching it up. You can see there's like deeper 850 moisture up along that boundary, deeper 850 moisture back south into Oklahoma. But there in Kansas, it's not looking so good. It's not looking as much, right? Well, here, I want to take this full screen because I want to point out something else. Why was there a robust storm in Oklahoma? Why did the storm updrafts in the Kansas, like southern Kansas area, struggle? Another thing, dry lines, how they're stacked. Very important. If you see that the moisture is overhanging the dry line back to the west like this, the deep layer convergence, when there's not a ton of upper forcing, is going to be way weaker. And that's a problem. You're not going to have as strong a pushes against any sort of capping if you don't have the convergence that you would down in Oklahoma. Look, down in Oklahoma, the dry line is stacked. It's like from surface to 850 and on up, there is moist air hitting dry air. But it's only happening really at the surface there in Kansas, which is an interesting problem because there's moisture along the dry line, but it's also not as good at 850. So these are small, subtle, super tiny differences. It's important to know. It's important to know. So if you're sitting here in the morning, you've got a choice, right? There's a boundary to your north. You can tell. I will tell you 9 times out of 100, if I'm not doing something like TV coverage, I'm going to the boundary every single time. If it's oriented to the right of the flow, the upper flow, and the upper flow isn't too strong, there's a lot of instability, a lot of moisture, those temp dew point spreads are small. That's where it's at. If but also I chased the southern target down in Oklahoma. It was really cool. Really cool supercell at dusk. It blew up at dusk. Amazing structure, produced an EF2 tornado after dark. So this isn't a drill. It takes a skillful eye to spot these things. I mean, these are small differences. This is a very this is stuff you got to look for. Satellite trends are important to monitor all day. We talked about a satellite a lot in this video, and I think there's a few things I hope that you picked up there that you can look for to spot some of these subtle differences between targets. Because you got to note these, because if you've got 2 or 3 targets you're trying to decide upon, these things could make or break that target. There's a lot of other things, so it's not just this simple. You got to think about storm mode, shear, all those things, but this is just we're just assessing soundings, just the very broad here, and you're already seeing subtle differences that made a huge difference. And also, sometimes models do not get this right, especially HRRR, but all models tend to struggle with dryline convection. They just have trouble with this. Hey, if you like this video, it's time to hit that subscribe button. Thanks for watching. This has been an amazing time. I love talking weather. I love talking observations. This is my jam. It really is. I love this. I love it so much. So hit that subscribe button. Leave a comment. Questions, I'll answer them. Maybe in a future video. We've got live storm chasing. We've got more education, a lot more coming. So hey, remember, this is important. Weather's for everybody. That includes you. I am so glad you're here. I'm so glad you're a part of this. And I am so glad you're going to stick around. We'll see you next time.